Thank you. Thank you, Eric, for the invitation and Raúl. Um, so as you were saying, this is a talk that is mostly related to stochastic optimal control. Let's describe it this way, particularly a variation of the usual formulation, right? So the title is quite a heavy, I feel like. So I'll go step by step. I will define what is a stochastic optimal control, the usual setup, the usual problem. Then I will introduce the methods that are used in general to solve this kind of problem. And then I will talk particularly about the new formula. I mean, not new, but the obvious formulation or the derivation in the case of partially observed stochastic optimal control. Where do we need it? Yes, and I will present the way that we solve our problem here numerically. So, first of all, we start with the most, let's say, basic stochastic optimal control formulation, which most of us should know, or if we don't know, it's quite direct. I will try to present it here. You basically have a process X, right, that describes whatever dynamical process that you need with this following SDE. And what you want to do is you want to control this dynamic. Now, the question is how to control this dynamic and for what purpose to control this dynamic. So you would like to introduce this control process that is called alpha T that will be able to somehow control your dynamics here, as you see in red. And the whole point is actually to minimize some sort of cost. So what you would want to do is you want to control your process X using alpha to be able to control these or to minimize this cost, or in a case of a reward, you can actually maximize your reward. You just have to define it the way you want, so either a minimization problem or a maximization problem. What you usually end up with is you end up with a control alpha that you follow your process. It's evolving naturally, following these dynamics that you assume in the first equation. And then you observe X. And then based on X, you would have a feedback law, right? It's sort of a closed loop. So you control and then you observe, you apply to the dynamics, and then you observe again. And this is why there is the word closed loop. So it's a function of X. It's a function of the state that you observe. And in that case, you will reach some sort of minimum of that functional J of alpha. Now, the question is how to solve this in general. One way to look at it is that there are two main approaches. Two main approaches. The first one is the Hamilton-Jacobi-Bellman equation, so the HEB equation, where you basically define a value function. And this value function is defined for all times between 0 and capital T. So this is the time frame that your dynamics evolve in. And you define this for all x's. So basically, at each time, you say, okay, I position myself at one point of time, and at any point of x, giving any point of x, what is the future value that giving this control, which is the optimal one, would be expected in some sense. So what you have giving this HEB equation is you end up with a nonlinear PDE that solves this for this value function for all time and all x's. So in some sense, it's a very, very strong object that will give you somehow a lot of information and actually more information in some sense than what you need because eventually, if you're solving the problem for X and you observe X, you in general will have particular paths of X. You don't need it for all the X's, actually. So here, as you can see, it's conditioned on xt equal X, but eventually, when you solve the control at the optimality, you will have paths that evolve in particular area of the grid of X. Now, this is the main approach, and the first one that was particularly a lot of people know about this and use it heavily. The only thing is how to connect this with the optimal control. Well, in general, what you do is you end up with a value function, right? And what happens is that at this Hamiltonian level, you minimize this pointwise at each time as a function, which would end up as a function of the derivatives of the value function and its second derivatives, Hessians. And then you can plug it in, you get the solution, and you plug in, and you have your alpha. This is the usual stochastic optimal control setup. As you can see here, the Hamiltonian always depends on the derivative of the value function with respect to x and the second derivative with respect to x. Now, there is a second approach, and one good way to look at this is actually you can think of the first approach as the primal method when optimization. So think about optimization, no optimal control. When you solve a primal problem, so we're using the primal method. And the second approach here, which is called Pontryagin stochastic maximum principle, is a method that is equivalent to the dual. So basically the Lagrangian method, the Lagrange multiplier method. So using the second approach, what you end up with is this forward-backward coupled system. I mean, you don't need really to focus a lot with what it contains exactly, but mainly what it contains is a forward equation. So you have a forward equations that drives the process X, and you have a backward equation that drives the adjoint pair here in this case, at least. And the outcome of it mainly is to think that this will give you only necessary optimality conditions. So they are coupled by this equation of minimization of the Hamiltonian particularly, and this will give you this particular structure of a forward-backward SDE. Again, this gives you necessary optimality conditions rather than sufficient conditions. And there is a slight link between these two methods, which we now identified, the first and the second approach, is that along the optimal trajectory, you will always have the relationship, this relationship that the adjoint variable is the gradient of the value function that was derived from the AGB method, and this only holds along the optimal trajectory. Other than that, things break in some sense. Now, why we introduce this is we just want to get a feeling of the methods that we are used to solve this particular problem. And here again, we focus on fully observed stochastic optimal control in these two approaches that I've just presented. So if you want to compare them, the AGB has this PDE structure, right? It gives you sufficient, so it gives you a lot of information. And what it gets you is if you go high in dimensions, this suffers actually from the curse of dimensionality, as you have to solve it on a grid of time and the state space X. So if the dimensionality goes high in X, you definitely fall into a bit of problems in some sense. Okay. Now, if you go to the stochastic maximum, Pontryagin maximum principle, you end up with these forward-backward SDEs. You have these stationarity conditions to determine the optimal control that couples them, but this will give you the necessary conditions, which will become sufficient if you have the usual convexity conditions. Again, think about it as if it's a primal or a dual problem, so you sort of close the duality gap to zero. Now, it is somehow simpler or easier to solve in terms of grids and time dynamics, but you have to also take care of the adaptivity problem because you have an equation evolving forward, an equation evolving backward, and they are sort of coupled, so you don't want to use information from the future in your control or while solving the problem. So adaptivity need to be taken care of, which is usually done by projections or conditional expectations, which also in higher dimension, this can also be costly. So it's a trade-off between two methods. Now, the question is, how does this relate to the partially observed stochastic optimal control? And first of all, what is a partially observed stochastic optimal control, and how do we define it in our case? Now, we actually assume the same form of dynamics, but these are hidden dynamics now. So you actually, when controlling, when it's time to control the process, you actually don't observe X. The variable that we want or the state that we want to control. On the other hand, what you have access to when controlling or when modeling your system is you have access to this process YTN. And now YTN comes discretely, right, at predefined time grid that you say, okay, it's an equidistant time grid. You have, I don't know, 4 observations. So you get one at each time. And what happens is that YTN is basically generated by the hidden the hidden state plus some external noise. So you add some noise to it, and you add also in our modeling, we add this beta particularly, which one should think of as another control, which will be here in our case as a discrete control. So the takeaway of this equation 5 is that you have these dynamics of a continuous process X that we are trying to control. This will be the main idea, where it is controlled by alpha, but then you cannot observe it, yet you observe y, tn, at discrete time points that will be a function of x, but it will be distorted with some noise. And that noise is also somehow controllable with this variable beta, or with this control beta. Now, it is useful here to define these filtrations just for theoretical reasons and just to try to understand here what happens. So basically, what you would have is you will have this Fy, which is the filtration coming from y. Basically, it's piecewise constant. So again, because you only have informations at these predefined discrete times tn. What you also can define as the filtration of x is, if we were lucky to observe x, we would be using this filtration. And then there is this joint filtration, which we call fxy, which is sort of very useful for theoretical reasons, particularly, where you actually kind of observe x and y, and we will explain later, because this sort of does not really make so much sense when you think about it. If I observe x, why would I need to observe y, right? I observe x, the perfect process. Why do I need to distort it with some discrete information? Yeah, these are just defined for this particular definition, actually, where we defined the control classes that we can use controls from. And here we denote 3 control classes. And a control class is basically the class of controls where we put all the conditions, what we are allowed to have as controlled. So if we work in the partially observed problem, you're not allowed to observe x, right? So you need the adaptivity to be restricted over the filtration f of y. So you're not allowed to observe x, definitely. Now, if we were, and this is UPO, right? PO is for partially observed, FO is for fully observed, where, again, you're only allowed to observe x, right? And x is enough to make your statement about any other control. Now, the UR, which is this class of new controls, is actually a control that can see X and Y. And we call it UR because of a particular reasons where we can actually look at this class of controls like if it is a randomized class of controls. And what do we mean by randomized? In general, when you are controlling a process, you can either control it in a deterministic way, in the sense of it is you have, let's call it a pure way, which is called a pure strategy. You observe the x and then you just apply it over as a function of alpha of x. Or what you can do is you can have these mixed strategies where you can add some randomization by bringing in a random variable and using it in making the control class. And this is the class of randomized control that is defined by x and y. And we will see later why we consider it as randomized if it's related to this filtration. Now, again, the whole point is to minimize some sort of cost or maximize some particular rewards. And here we introduce a new control, which is beta, the discrete control that I've just mentioned. Now, the question is, you need to outweigh this choice of control by a particular cost because yeah you introduce a new control, so we need to make sure that we know what kind of meaning what kind of meaning it does have. So what we have is we have the usual continuous control where you want to minimize over a running cost, right? That depends on the x and alpha, which is the continuous control that you can control all along the trajectory. The final terminal cost that existed in the fully observed case, but now we introduce this new discrete cost that is related to beta. And one way to look at this beta is that think about it as a penalty term, in the sense that if you're going to observe, back here to the observation case, if you're going to observe a very good observation of x, meaning that I reduce the level of noise for some reason, you would probably need to pay more cost for this. Then, if you observe a more distorted picture, you probably pay a less expensive cost. So this is the trade-off. I want to observe perfectly, I pay a lot. I want to observe somehow with noise, I pay less. And then you can get to choose this trade-off. So this is what you can say as, yeah, it encodes the sensing effort or the precision. And if you think about this in actual real world application, you can be a submarine, for example, that is working on the underground, and you really don't observe what is being sensed on the underground in terms of positions, but you can sense some pings in some time intervals. And if you send a very good signal, then you use a lot of battery, which you are not allowed to use too much battery because you have a mission to finish. But then if I send a good information, there is a trade-off, right? Because I pay out of that battery, so I need to send information in a good way, in the terms that I trade off the quality of information and the quality of control that I will have given my cost. So this is just an analogy so that we understand how can this be applied in general. So you're trying to minimize that cost. Now, in my title, that is the word belief state. And this is quite important because to solve such problem, if you recall, the value function previously was a function of x in the fully observed case. Here, we cannot observe x. We cannot really condition on x when solving it. So actually, a smart trick that is widely used is to transform the problem into a belief state problem. In the sense is that I used to have an x, now I will have my belief over x. And that belief of x is you define the law, the conditional law, which is called the filtering distribution, because here we're coupling between two problems, right? We want to control, but we want to have a filtering, and we want to have an estimation problem at the same time. And we're juggling between them. So if you define the belief as being the law of x giving all the given observation up to this time, where this yn vector denotes all the given information that was brought to us at this point, is you will have that between these observations, you will have a deterministic flow. And the sense is that you will have deterministic dynamics that are governed by alpha, and they are governed by the Fokker-Planck equation, right? That is evolving here. And this is nothing but the Fokker-Planck equation with a generator controlled by alpha. And then what you just have bias updates at the observation time. So a new information comes in, right? You have a prior and you will have a posterior, and you just update this prior by getting the likelihood and calculating this bias update. So basically what you have is you have this between the observation, this continuous or continuous deterministic dynamics, which is the deterministic flow, and you have the bias update at the time of the observation. Now, why this formulation can be interesting is because from transforming the problem to a hidden state problem where the x was unobservable, now what you see here is you can transform the whole problem into a stochastic optimal control where the state is the measure. So we went from x to the probability of x, kind of, right? So the measure of this, the probability measure of this process. Now you can redefine all the problem, right? To write it down as a value function, for example, or a cost function here as a function of mu. So you before we used to condition at xt equals to x, and as you can see here, the value function is long, but it's okay. Just think of what are you conditioning on. And now you're conditioning over this probability measure that is parameterized in y, this conditional probability measure. And as you can guess, if we want to use the same approach, the same first approach, which was used in the fully observed case where we had this nice HGB that behaves in derivatives of x. Now, what you would have out of this is you would have a functional. It's no longer a value function. It's a value functional because now it depends on mu. And mu is an infinite dimensional space. And what you have now is you find yourself taking derivatives with respect to mu as you expected before, because we were taking derivative with respect to x, and this is sort of the analogy that drops in here. And obviously, you have this jump condition at the time of observations that is coming from the discrete cost, because what happens is if you think of dynamic programming principle, if you go backward, you sort of at Tn minus, you sort of need to add the discrete cost that was not included in the future cost. And what you're doing is you're averaging over all possible observations that you are getting. Now, nicely enough, if you can transform this mu that used to be defined over the probability measures to a finite dimensional space, you're lucky because you can solve this AGB in a very, let's say, more it's more tractable in some sense to be able to solve it because it comes finite dimensional in this case in the moment. So for example, if you have Gaussian dynamic, if you have Gaussian distribution and you have linear dynamics, for example, so the state stays Gaussian over all the times, even when controlled, then you can actually just summarize all the information in the two first moment, and they become sufficient statistics to be able to represent the whole probability measure mu. And in that case, it's solvable. Otherwise, it can be very, very tricky to solve this HGB particularly. Yes. So our way to solve it is, first of all, I would like to define a particular point is just on how to derive what we call the Pontryagin maximum principle. So first of all, we define these cost to goes. And the cost to go is basically, you can think about it as the expectation of the future cost giving xt equal x here, giving a particular state. You would say, how does this difference to the value function? Well, the value function is the infinimum of this, right, if it exists. So here we define the cost to go for the fully observed problem, because here it's given x, right? You are observing x, and this is the control that comes from it, right? This underline u, and this is the optimal value for all given x's. So if you look at this plot, basically, you just have for every x, and you fix one time, right? Here, the plot is just for the sake of understanding of at one particular time, is that you are observing everything, so you have sort of a lower bound here. Now, what you can do is you can define also the state, the cost to go for a partially observed problem. And in that case, you are only allowed to observe the observations vector yn equal to y, right, for a particular one. And u tilde will be the optimal control that is derived in that class of controls where you are only allowed to observe this observations. And again, you can define for the same classes, the different previous classes, the randomized cost to go, which will depend on x and on y. And here again, it will depend on x and on y, so it's conditioned on x and y. And this is the expected value of the future cost from that time. Now, what you can notice is that actually the class of partially observed control is included in the class of randomized control, and this is giving the fact that this was generated by the joint filtration, right? So every element in the partially observed controls is in the randomized partially observed controls. So what you can do is you can take any control from that class, right, and plug it in into the randomized class of controls, into at least the randomized cost to go, because simply of this inclusion. So you can define the realized pathwise values that is induced by u tilde, right, coming from the partially observed, but you apply it over the randomized cost to go. So what would happen is that the optimal cost to go from the fully observed is definitely better than the randomized one, using the optimal control that was derived from the partially observed case. And what you have here is for a particular fixed yn, you would have that this is always greater or equal than underline u for the fully observed one. But what happens here is that the points here that are used for x are actually following a probability measure mu t. So what you're interested in is you're not interested in this x because you cannot really observe it, so you need to integrate over your belief. And what happens is that while integrating over it, what you recover, actually theoretically, is nothing but the value function that we have just defined over the space of the belief state. And why is this particular formulation interesting? And why I said, okay, this is probably the randomized one probably does not make sense, but using it here really does, is because this cost to go is nothing but a linear inner product with mu. And as we said again before, is that the derivative of the value function with respect to the state in general gives you on the optimal trajectory will give you an idea about the adjoint variable. So what you can notice here is that if you take the derivative of this value function, right, with respect to mu, what you're left with is this u randomized that was using the partially observed control, the optimal one actually, but this will be our new adjoint variable, actually. So this is the interesting part is, yeah, again, as I was saying, this brings you to this key kind of equality or inequality because it depends on the case of the necessary convexity, right, conditions. But if you do any needle variation argument or a Lagrange multiplier method, you will end up with a control that satisfies some necessary conditions, particularly, right? Because you have these local optimality conditions, right? That will give you this optimal control that is defined using the adjoint variables. And this will end up to this forward-backward system that is here defined pathwise. What do we mean by pathwise? It's because this is kind of parameterized in the y's. Now, again, this is a very scary system when you look at it this way, but what is it? It is basically a backward equation, right, for the adjoint variable that interestingly enough, it is also the randomized cost to go that was defined for the problem. You have the forward dynamics, right? These are the forward dynamics of the mu. And these are the jump, basically the jumps at every time. So this is the jump forward, this is the jump backward at the time of the observation. And they are coupled by these two control choices, right? You have this controls that satisfy this optimality condition. Now, this is an alternative representation for the Pontryagin maximum principle. It's a different formulation, but this u is nothing but the derivative of the value function when the state is a belief, right, a probability measure. And you can actually even write this in Hamiltonians and have the usual formulation. And this has to be solved as a forward-backward system because they are definitely coupled. So one trick here is that The system actually, for example, it depends on x and yn. So the variable here depends on x and yn. And n is the number of observations that you have up to this time. The issue is, if this number of observations increase drastically, there isn't really a tractable way to solve this problem, and yet, unless you have an exact formulation on how to solve it. But numerically speaking, this problem we have the intuition on solving it with an L2 regression method, so using this Ys. So if the number of if the number of observation increases, the dimensionality of the problem actually increases heavily, right? And what you want to do is you actually want to somehow compress that information. So you can think about the vector y of a vector of informations, right? But what you want to do is you cannot really look at the full history. What you can do is you fix a window length. For example, in this example, it's equal to 3. And what you use is that each time that you advance in time, you leave one observation behind and you get the new observation. And this can become very interesting, particularly right now is the idea is to put some window length, but at some point we can have it as a control in the sense that you can think about it. Well, what if I have a high dimension, but I observe in a window length of 3, right? But this process itself has 3 dimensions or 2 dimensions. Maybe one dimension is much more important than the other one, and I can ignore that one. So maybe it becomes slightly selective, which can be a very interesting actually derivation of this particular compression, is how to compress it perfectly to keep the biggest amount of information. Obviously, having a window length and forgetting about things can have an issue of sub-optimality, but at least it will give you an optimal control that you are able to use in such a setup. Now, how was this solved before, at least in this setup? There is something that is called the separation principle, which is actually quite intuitive, right? If you have a problem where you cannot observe what you are controlling, what you can do is I can assume that I observe what I'm not observing or what I'm controlling, solve the problem like if I knew the state. So basically, you end up with a control with an alpha where you have a control, a feedback law of xt, for example. But then what you do is I don't have xt when I want to apply the control. What I will have is actually I will have an estimate. So what you can do is you can plug in the best estimate that you have instead of using xt. Now, this is called the certainty equivalence, and the idea is to separate the two problems between the problems of control and the problem of estimation. And then you can solve them sort of separately, and then replace the state with actually your best estimator. This can work, and actually it is true. It gives you the optimal control in the case of linear dynamics, right? If you have this linear dynamic setup, but it is not correct. So this separation principle does not hold if you have nonlinear dynamics or structures of costs that are non-quadratic, for example. So you cannot do it. Also, it is not feasible if you're controlling the beta, for example. Why do I say this? Because what I said before of having this separation principle, the separating the estimation and the control cannot be done. Why? Is if I want to first of all, what I do, I want to control perfectly like if I observe. In that case, what would I choose the beta to be? For example, if the beta is the level of noise in front of a white Gaussian noise, what does it mean to choose beta like if I observe X? Beta is the level of noise of observation of X. So if you observe X, this does not make sense and you fall into these pitfalls in some sense. So this will be very useful for us, though, the separation principle, to be able to compare our algorithm in the linear quadratic case, at least. So the question is how to solve that forward-backward system. Well, the idea is, again, we want to learn a set of parameters that we give for an ansatz of that function u, and we will use particular trajectories, right? We form trajectories from the given prior, And we use these costs that are induced afterwards to be able to train it. And what does that mean? Well, no, it goes like this. So basically, what we'll do, we will use a particle scheme for this fixed point that we call theta right now. So the idea is, as I said, to define an ansatz, right? You define your ansatz for all times defined by theta k. So at the point zero, at the first time, theta zero. And for each interval between the first observations, what you do is you have m particles that you start with at time zero. You evolve them at each discrete level of your discretization. This is irrelevant. This is not related to the times of the observations. So this is a sub-interval that is between, for example, 0 and T1. You discretize it, and then you evolve your particles, and you calculate your optimal controls based on those particles by doing this conditional expectation and using the L2 regression method. Then, as far as you're concerned, once you reach the time of the observation, you need to make a control over beta. So you do the same action, right, to pick up beta accordingly, and then you generate the y's. What happens here is that you keep doing this for multiple subintervals, and you end up with m trajectories, and you have pathwise costs for each trajectory, right? So you include the running cost, you include the discrete impulse cost, the terminal term also. And then what you do is you update your parameter theta based on these aggregated costs that you had from each trajectory. And then you do this again until a particular convergence is achieved in some sense. And this is the numerical way on how to do this, right? So what I want to present right now is I want to present some numerical experiments that we have done to compare our works at least with the separation principle, for example, when it holds and when it does not hold, what we do. So first example, which is the most evident example, we consider the linear quadratic Gaussian example. So you have linear dynamics, right? And you have Gaussianity. So x0 follow a Gaussian at the time of the start of the dynamics. And we do two variations, first of all, because we cannot use separation principle in the second variation, actually. So the first thing first is to say, well, we do not control the noise level. At some point, the noise level is given for you. You just have discrete input that you cannot control, but you can control the process and you cannot observe it. So what we do actually here in this case, you would be removing the discrete cost that we have introduced before for beta. So this is the first variation. And why we do this again, because we can compare it with the actual solution of the problem. A second variation, which we call here the variation B, will be a case where we can control the level of noise. And we will assign a discrete cost for it. So again, if beta is extremely high, this will probably mean that the y is irrelevant, is not giving us a lot of information. So the cost is going to zero, right? If beta goes to zero, this goes sort of to infinity. And this means that your y here, beta is equals to zero, means that you observe a linear transformation of your x. So basically, you can recover x exactly at that time of the observation. Now, the point is, again, to minimize g of alpha. That is quadratic in the control also, quadratic in the final, and this particular quantity that either we keep with the first variation or we remove with the first variation. And these are the examples for example, in the case of one-dimensional dx is basically the dimension of x. So what you can observe here on the left side is that you have a fixed noise, right? You cannot control it. You only control the dynamics. And what you have is you have the cumulative cost. Here, as you can see, this is a problem where you actually only observe at time 0.5. So the number of observations is actually equal to 1. And what one could expect is that as much as you have more observations, even if they are noisy still, you would actually have a better and a better and a better cumulative cost. So the cumulative cost, just so you know, this is this value here, like the value that is given here is nothing but the integral over 0t of the running cost plus the terminal cost, right? And if you move, I don't know, for example, if you move here, this is nothing but the integral from t to capital T, right? Just to get a sense of it. And this is why it's just it is decreasing. And as you can see, if you go to a number of observation that is equal to 30, even though you have noise, you actually get closer and closer to this blue curve. And the blue curve is nothing but the fully observed stochastic optimal control. So it's the cumulative cost coming from the case where you can actually observe everything. So you can see that, okay, this actually, this was sort of a sanity check, right? You can sort of get a meaning out of it, out of this plot. And again, the same exactly here goes for a particular path xt where we have the same uh, Brownian noise, definitely, because we want to compare the same cases. And what happens here is that our control actually what it wants to push the process down to zero. And what happens here is that if you have one information here, only one observation as the green plot says, right? You sort of get a delayed information. So you only try to push it down afterwards. Now here, if you're having more and more information at the beginning, then you're trying to do this better and better. And again, the purple plot here in the purple is for 30 observations, and it's getting closer and closer to the fully observed case. And by the way, I probably didn't mention this at the beginning. If you have any questions, please interrupt me. So no issue of interrupting me in the middle. Yeah, a little bit late, but still, you still have time to interrupt me. Yeah, so again, the linear quadratic case and the first variation can be compared to the separation principle. And yes, we do compare it for different values of the number of observation. As you see, the particle method is actually, really, really close to the value that is given by the separation principle, even though that in the particle methods, here, for example, you have 30 observations, but still we only actually look at one observation. So the y is equal to 30 at max, right? Here in this case, the y is equal to the length of y at least, huh? If we can put it this way, the length of y is equal to 30, but we are only looking at one observation in this case. So the linear regression is much simpler to solve, right, on a one-dimensional case then. But still, it is close, really close to the separation principle that gives you the optimal value. Okay, so the 1D case works. You can definitely do this for multi-dimensional case. But let's go to the interesting point where we introduce beta, right? This is where the model becomes more, let's say, informative. You can make a little bit of conclusions out of it. And this is the problem where we introduce the discrete cost. Now, as you can see here, there is this jump in the cost, right? I will try to zoom so everyone like sees particularly the the plot. So there is this jump of the cost. I mean, a lot of people say, okay, what is happening here? I mean, it's simply that you used to have this integral, right, t and t, and now you have a jump that is only happening after t equal to 0.5, or yeah, that is included in this interval. So once t is greater than 0.5, you don't have this jump. Once you pass it, you actually have this discrete jump. So it is totally normal and predicted to see such jump. So what do we do here is we control alpha and we also control beta. Okay? And the conclusion was that the main point of optimal control is basically to minimize the whole cost from 0 to capital T. And this is what happens, right? This is in red is the cumulative cost for the problem controlled with alpha and beta, which is we found that at that point we have only one observation. So the level of noise is equal to 0.7 we found in our derivations. And what you get is if you change that beta to another beta, right? Whatever fixed noise of level, and you recalculate the optimal control alpha, you always find that, and obviously you consider the cost, the discrete cost of that, you always find that the cost using the beta is include the informations, what you have is you have the dynamic programming principle, obviously clearly done. Um, it's a real example of the dynamic programming principle in some sense. Is why? Because at this level is the time where after you had the observation. So it is the cost after you have the observation. And then what you notice is that you will always see that the the blue plot, for example, the blue line that has beta equals zero point 0.3 is the lowest level. And why? It's because beta is equal 0.3 is the least level of noise that you get. And then again, for the green beta, right? The green cost coming from beta is because it's equal to 0.5. Again at 0.7 and again at 0.9. Yet before it becomes different, right? Because this great observation that you used afterwards has a cost. And as you can see here, the biggest cost goes for the blue curve. The smallest cost goes for the yellow one, but yet still it wastes some information in that case, right? So yeah, this is kind of a very good example to see what is the meaning of these costs and how do they make sense. Now we say, okay, if you have one observation, the actual beta will only depend on a particular. It will be a constant. It will be a scalar, right? Because beta does not. I mean, beta you decide to take it before observations, right? So if you have one observation, before that observations, I had no other one. So beta is a scalar if I determine, so the first beta is always a scalar. The other betas will be functions of the previous observations, like it or not. So this is what happens when you increase the number of costs, and then you also have to do a regression over beta, not only alpha, because beta also becomes a function of the previous observations. And again, we try this, we do the same test, at least on the left side. You have the same conclusions that you can draw is that using that optimal beta, you have an optimal alpha also that gives you the lowest value for compared with any other beta that is selected for all the other observations. We were also lucky enough to have our previous work collaborators that worked on this with Elisa and Boalem on the topic of AGB, but in particularly in the case of Gaussian distributions, and a solution using HEB was available for us. So if you compare the values of betas, and here not only the values, here why I say values, because the first beta is one value, and here, as you can see, it's sort of a distribution, but it does not vary that much. As you can see, they are in some sense they relate to each other, right? They are similar in terms of the level, right? The values that you get from Pontryagin are quite similar for the HEB, even though that the problem is probably not convex because the introduction of this new discrete cost that was given. So you would not expect exactly to have the values, but you would expect something in the same order, right? Which is the result that we had over here. Now, again, we increase this dimension to up to the level of 10 with also the same observations that we get. I mean, the same observations or remarks that we get on this numerical example. Obviously, we couldn't compare this to HGB because yeah, with the dimension of a state going to 10, that will be very challenging to solve the PDE on that particular plate, if not impossible, actually. So yeah, you get the same constatation, right? The level of the noise chosen by beta and alpha is also always the lowest level using this particle method here. Now, the last example, which I think is quite important in the setup, is okay. You can do linear quadratic. You know, linear quadratic is always nice, but what if things change, right? We wanted something more, let's say, challenging in the sense for the algorithm to be tested on. And we found this very interesting, actually, example that sort of mimics, you know, this kind of trajectory followings or these barriers that you kind of build by introducing a a kind of a penalty function or a potential function in the cost. So what it does here is everything is quadratic in the previous sense, right? If you see the costs, but what you have here is you have a penalty function. And this penalty function, what it does, it's basically what it's doing is penalizing the existence, I mean, highly penalizing you passing by particular regions in the space. For example, here you have a high penalty of the order of 1,000 if between these times, right, you pass by a particular by particular cylinder, for example, in the space of a hollow cylinder, actually if you pass by a particular and the plot will explain it further to you. Yeah, the dynamics here are still linear, but what we do here is we break the quadratic cost that actually in the separation principle is very important in some sense, right? Here we keep the noise level fixed at some level of epsilon, but the nice thing about this example is that you can observe what is happening for the trajectories and if it is actually avoiding that penalty region. So this is the example in one dimension, and you actually only observe it at time equal 0.5. So you only get one observation at time 0.5. What you get here is actually a prior. So this is a set of trajectories that are evolving, huh? And they evolve from time 0 to capital T while trying to avoid this trajectory, huh? And the penalty is very high here. It's like at the order of 1,000. And you are not observing it. You're not observing it. So you're trying to move a cloud of particles, if you look at it at each section here, with trying to avoid this. And what can be very interesting is this particular path that is slightly bolder in black, is that this point is the point of the observation. And as soon as the profile, as soon as the operator observed, right, this is the only information that it had at that point, is that at this point, he observed that it's more or less close to this area. So what he did is he, like all the particles that were hitting it closer here, they tried to avoid this path by acting on a particular level of alpha that is probably high in that sense to push it away from the penalty region that has a very high penalty. This example was also solved in the same case for a 10-dimensional example. Yeah, but the only thing obviously is you cannot observe this in 10 dimensions. So what you have is you have the norm of x that you are trying to avoid, right? If you want to generalize this penalty function, right? Yes, and this can be very interesting because sometimes you want to control things that you do not observe, right? And you want to you want them to do some sort of particular mission and you want them to avoid particular boundaries, but you cannot observe it, right? So you need to make sure that you are controlling such thing. And this is why I believe this example is very informative and very nice, actually. So yeah, and other than this, like one of the things that I'm like looking for in general is actually to find more and more applications for this particular example. So please feel free to reach out at any point, even later if you want to talk on particular applications, real world applications of such modeling perspective. And yeah, the preprint is available now on archive. So yeah. So I'm happy to welcome your questions. Yeah, and thank you, DFG, for the financial support. Yeah.
Thank you, Saif, for a very, very nice talk. Do we have a question from Alex, for example?
Yes, I have question. Thank you, Saif. Can you please go to numerical examples and assume that I am decision guy who take decisions? What I can, not previous one, previous, yeah, this one, for example. Yeah, this yeah, all these pictures. What I can learn from this, which useful information I receive from these graphics?
Well, you as a well, let's say it depends on which variation we're talking about, definitely. But what you can get out of the graphics is that you know that your algorithm is actually working, right? Because you get an optimal cost that is below any other cost using any other betas or other control, randomly selected or chosen in a different particular way. But what you get as a controller eventually is you will get the alpha as a function alpha that will depend on the observations, or beta also that depends on the observation. So you will get a set of functions, and then you just observe what are the incomes of such observations that you are receiving at each time point, and then you just apply them. You apply it the way it is. So this is more or less the output. If you wanna highlight the output of the algorithm is a control, right? Yeah, I hope that answers your question. Otherwise, maybe I can develop further if you want to ask again.
So control which is parameterized by constants alpha beta, yes? Or
No, so you get a control alpha, right? Alpha is not a constant. Alpha is a function. So maybe I write it down here. Yeah, or maybe I go back to the actual numerical example, right? So as you can see here, alpha is there is a variable here, right? There's this z. So basically, you'll get an alpha t that depends on that z, and z is the observations that you're receiving.
okay.
And you will get the beta as also a function of z. Well, if you have one observation, beta will be scalar because you observe nothing before controlling beta.
Okay, it's why in one of your numerical experiment you had only one observation, yeah, I think.
Exactly. So this is the difference between, in this numerical example, let's say here, beta is a constant, beta bar is a constant, and this is why beta here is a function of z. It's because this beta works on three observations. So when I pick beta here, I had no observations before, so it's beta. The first beta is a scalar. The second one will depend on the observations that I got here. So this one will be a function of the previous information, and this one will be a function of both, right? Z1 and Z2. I hope I made it clear.
Yes, thank you. Thank you.
Yeah.
Okay. Do we have any other questions? We have time for maybe a fast one. Andre, yeah.
Hello, Saif.
Hi.
Very good talk.
Thanks.
Very interesting for me as I am starting to learn more about stochastic optimal control and all. Question I had for you. I see you have a very general formulation in terms of your value function. And you have your control on the observations as a control over the noise level, right? But this seems like a choice of yours. Would your framework also work, say, if you had some control over the time of the observations? For example, say you have some horizon and then you have a fixed number of observations, then you're trying to find when possibly on the fly, what are the good times to observe?
Yes. So this is actually a very good question regarding this, because as the beginning I said, I have predetermined observation times. You don't get to determine them. One of the ideas is that at this general formulation, this is not embedded. The only thing that you can do actually is have another control that says, okay, I have a time grid. It is predetermined in some sense. We make them more frequent, let's say. But then I have the control beta, not only that controls the level of noise, but controls if I do that noise or not. So it's you can introduce another, right? A kappa that is a binary variable in the sense that if it's equal to 0, I do not control. I do not observe. So I get nothing out of it at that point. In that case, the level of beta that you will get is irrelevant, right? And if kappa is equal to 1, then the level of beta will make sense. So in that case, I will be choosing what to control. Now, the question is, this still is a fixed time grid. You don't get to choose the time, yet you get to choose which time to control over, if you see what I mean. Changing it into a problem that becomes, oh, I want to pick the time, right? Whatever it is, not out of a given grid. may become slightly challenging as it sort of becomes an optimal stopping control time because the structure of your forward backward PDE or forward backward system that you were solving, if I can come back to it, actually these will be sort of variables based on your control, and that can make it complicated. At least in my humble opinion, with what I know now.
Yeah, that's exactly what I thought would happen. It would have all this, how to keep track of all the results of these
Yeah,
controls, right?
yeah, exactly. How to keep track of it and how to embed it in the algorithm, because at some point you have to solve these partial observations, and yeah, it becomes tricky.
Okay, I understand. Thank you very much.
Thank you for the question.
Okay, I think it's time we wrap up. So thank you again, Saif, for the nice talk, and thank you all for attending and for your questions. We'll see you again next time in a few weeks, as announced on the schedule.
Bye bye. Thank you.
Bye.